Good morning, class. Today we'll be having our last formal class where I'll be giving you some information. The next class will be a review. The topic of today's class is kind of generic, more on quantum mechanics, where we'll talk about all the exciting things that you will do in the future, potentially. Well, most definitely when you continue your quantum mechanics studies. This will be more or less a survey, and some of the things will not be on the final exam, but will be interesting things to look at. But as always, I'll begin with a brief review of what we did last time. Okay. So we talked about angular momentum and spin for the past few classes. So let's review orbital angular momentum first. Hamiltonian for that is that original Hamiltonian kinetic term plus potential energy term minus this new term, u naught v. And that h naught is for the hydrogen atom, the kinetic energy term plus the potential term, v of r. This is representing the motion of a charge around a nucleus. In the presence of an external magnetic field. There's this charge Q, which for hydrogen atom is an electron, just moving in an orbit around the nucleus. And this is where this orbital angular momentum arises, from this orbital motion of a charge around the nucleus. We found that the total angular momentum, L, has eigenvalues square root L times L plus 1 times h bar, where L is 0, 1, 2, 3, and so on. And we can write this term minus mu b as minus g times q b sub z qm naught, this looks like the Bohr-Maclaurin term, times L sub z, where for the orbital motion of the electron, g is equal to 1. Okay. So for the example of the hydrogen atom, Hamiltonian becomes, or maps to E sub n minus, that's the original Hamiltonian from h naught, and it's a term from the orbital motion, or plus rather the term from the orbital motion, which is minus qbz over 2m naught times m h bar, where m here is the quantum number m and not the mass, and this is the mass, and the m naught is the mass. Okay? We also considered the spin. Contribution to the Hamiltonian from the intrinsic spin. And let's consider a case where L is equal to 0. So the orbital motion term is quenched. It goes to 0. And again, the term in the Hamiltonian is, the new term is minus mu dot b. For the intrinsic spin, it became minus g q b sub z over 2m naught, the mass, times s, the quantum number h bar, where s can take on values of plus or minus 1/2. We found that for an electron, G is equal to 2. And for a proton, we were told last class that G is equal to 5.6. Okay, and this is something we determined from the experiments in the last class. Because electrons have spin and they can interact with the magnetic field, there is this term that arises called the Zeeman effect. And the Zeeman splitting we found arose in the Stern-Gerlach experiment. Recall, we shot our silver atoms through an inhomogeneous magnetic field, and we found that there are two components, or two spots on the screen measuring the impact of the incidence of the silver atoms. And that looked something like the following. Okay, the impact of the intensity of silver atoms striking screen looks a bit like this. And this is due to this energy level splitting arising from the presence of the intrinsic spin. Okay, and we can define omega naught as shown here. Okay, so that was what we talked about last time. As we found last time, there are a few applications of intrinsic spin. We talked a little bit about NMR, nuclear magnetic resonance imaging, and MRI, which is a variant on that. There's something called giant lead resistance, which we're all familiar with, or GMR, because it's the effect that's used to write data to our hard drives. And we also talked about in the future, people are interested in building quantum computers, and the spin properties of electrons is essentially the thing that will allow for quantum mechanics to implement, or understanding quantum mechanics, the material that can implement quantum computing, or quantum computations. So let's write those down. So NMR, GMR, and its implementations of quantum computing all rely on applications of spin. So consider how small is Hamiltonian. You can write this as omega naught S sub z, where omega naught is minus g times charge let's say we're having a proton, then G is 5.6. And then this gives rise to a two-level system in a magnetic field. With states at eigenvalues plus h bar over 2 and minus h bar over 2. And the spin splitting is omega naught. Now this delta E is h bar omega naught. And an experiment that takes advantage of this spin splitting is one that has some light with energy h bar omega naught incident on some distribution of protons. And we have this incident on some screen that's used for imaging. Okay, let's turn our attention to the first in-class assignment. When we return, let's move on to looking at another application, which is for computing. Let's consider first kind of a conventional computing. We'll look at conventional computing. And this involves binary digits or bits. These ones and zeros that you've probably seen or heard of before. Okay, and what one can do to create the architecture, create these bits, to generate these bits, is have a transistor, and the transistor can have a geometry kind of looking like the following. So there is source and drain. So current goes into the exit, goes in and exit through the channel. The source enters the drain. This object in the middle is the channel, and up top is the insulating material. Here is a bit of metal which comprises the gate. By changing the current here, a voltage applied to here, change gate voltage across the source and the drain, across the channel, and you can either have current flowing or not flowing through this channel, and this is allowing your switch to be on or off, represented by ones or zeros. That's roughly how it works. Now for the case of quantum computing, in particular a two-level system. Comprising qubits, where we have states chi plus, you've seen before, and chi minus. These are like up and down, so like ones or zeros. But what's different from the conventional computing case is that you have, with quantum mechanics, you have linear combinations of these eigenfunctions. So you can have a state, it's a linear combination of these eigenstates, producing a new state that is different from the ones that we had before. So you don't just have 1 to zeros, but you can have a linear combination of 1 to zeros. So because there's more opportunities, there's more chances to store information. Okay, we define chi plus and chi minus as these states in half, 1/2, and for chi plus, and 1/2, minus 1/2 for chi minus, and these corresponds to the S and M sub S. So S, first index, M sub S, the second index. So in general, you have some state psi, which as you said can be a linear combination of the eigenfunctions, chi plus and chi minus, and alpha and beta can be complex. So therefore we have a situation where we have 4 variables existing. That's more opportunities to store information as opposed to just 1s and 0s. And the similar usual rules hold. The sum of the coefficients must be equal to 1. And where the state is a sum of eigenstates, the wave function is a sum of eigenstates. And in the forward case, we know alpha squared plus beta squared must be equal to 1. So as I said, some of the probabilities, or the coefficient squared, must be equal to 1. So let's try to make this we'll put this in a graphical, pictorial representation. So I'll attempt to draw a qubit. I'll introduce this idea of a block sphere and how the state might live on a block sphere. This one here. Okay, so let's start by drawing that block sphere and explain to you what that means. So this is our block sphere, and on it lives 2 states. In the plus x direction, there's your chi plus, and the minus x direction, or rather plus z and minus z direction, there's chi plus and chi minus. consider some vector on the sphere. Pointing in this direction. And let's define angles, theta, and let's project this vector onto the x, y plane. Let's say it's about here. And this angle here is phi. Okay. And what we can do is describe our wave function psi in terms of a block sphere, and we can write psi is equal to cosine of theta over 2, where theta is this angle here, plus e to the I phi times sine theta over 2. Okay. And we can also write this in kind of matrix notation, where 2, 1, 1 is just the sum of the up and down states, chi plus and chi minus. Okay, another example of manipulating spin states. We talked about a little bit before. It has to do with entanglement. And in this case, you can entangle 2 qubits. So that a measurement on this qubit will give you information on this qubit and vice versa. Okay, let's take a look at in class 2 and 3. And when we come back, we will explore some material that's very interesting, but will not be on the exam. Okay, it's not on the exam, but it's still pretty interesting. Not on the exam number 3. Okay. So one interesting thing that we haven't talked about much, but a little bit about, is this impact of spin-orbit coupling. What is that? What does it mean? Let's talk about it a little bit. So let's consider the hydrogen atom once more, or hydrogen-like atom. Okay, and let's look at the rest frame of the nucleus. Has charge C+, and the electron is moving around in its orbit. Okay. Actually, let's put this picture on the next page. Okay. Great. Okay, so on the left-hand side, we have the nucleus rest frame, and on the right-hand side, as far as over again, let's consider the electron rest frame. Remember your special relativity. Okay. And in the case for the nucleus's rest frame, we can think of the electron orbiting the radiating current, and we get some magnetic field. Let's represent that as the following. Tiny magnet. Okay, not the best true line, but with its magnetic field lines. And in the electron rest frame, the electron is at the center of the orbit. And if you're sitting at the electron, you see the nucleus going around. Okay. And let's attempt to draw that effect following picture. The nucleus is moving around, generating the current this time. And again, it's called a spin-Hilbert coupling effect, and we can write it down by starting with this mu dot b expression. That's going to be due to the spin coupling to the angular momentum. Again, this is called the spin-Hilbert interaction, the spin-Hilbert effect, the spin-Hilbert coupling. Okay, so this is a little bit addressing the effect of special relativity, which certainly plays a role in quantum mechanics. We pretty much ignored it up until now. But we can say a little bit more about it. Okay, so when you combine special relativity with quantum mechanics, you get something called relativistic quantum mechanics. And just to give you a really brief introduction, without going to really any depth, you have the energy taking into account relativistic effects. So for instance, energy is given by p squared c squared plus m squared c to the power 4 all square root. Where the momentum you use in your equation is related to ddx from before. And instead of the Schrödinger equation, we write down the Dirac equation. I'll make something like this. Just to highlight how different it is from the Schrödinger equation in its structure. The factors of C show up, and then point out that these alphas and betas are these 4x4 matrices. If you consider the example of the spin 1/2 particle, with g factor set to 2, then our eigenfunctions become these 4 vector objects, where psi 1 is 1, 0, 0, 0, psi 2 is 0, 1, 0, 0, psi 3 is 0, 0, 1, 0, psi 4 is 0, 0, 0, 1. Let's take a pause and do in class 26.4. And that question is linked to spontaneous emission. In a hydrogen atom, as we saw a few classes ago, if you excite electrons in a hydrogen atom in a hydrogen lamp, for instance, you would get emission of light. It will glow at different wavelengths. This is due to spontaneous emission. And what does that mean? It's when you have a two-level system or two energy levels. Let's call this E2 and E1, and this system isn't in this excited state, and there is a mechanism with which it can relax and emit a photon. Okay, that's a frequency matching the energy level spacing. And to understand this behavior in great detail, we have to turn to quantum field theory, which you can enjoy learning when you reach grad school. Okay, so that's it. Kind of a very brief review of what we will look at in the future, and just pointing out some exciting things to look forward to. Looking forward to seeing you in the next class. Until then, be well.